Hello, my name is Colin Davidson. I'm bringing you our regular show, Unwind, every third Saturday of the month, except for this Saturday, but should be every third Saturday of the month. I'm one of the staff of the Handmade Network. Handmade Network is a big Discord community with a bunch of jams and events that we do on a regular basis, and a strong connection to our good friends over at Handmade Cities, who does a series of conferences twice a year. There should be one coming up in November. More on that later. I think we've got a jam coming up here soon too. So I will get you notes on that at the end of the show. So today we've got a special guest. Special guest is Konstantin Nandakke over on the Discord, talking about running ML models in a tiny amount of C. So I'll head over to our good friends. All right. Nandakke?
Hello.
There you go. You are live, my friends.
Hi, everyone. Am I supposed to hear myself right now?
Are you hearing yourself?
Yeah.
That's odd. Are you hearing yourself through me or through your stream?
I don't know, but
Are you watching on Twitch?
before I opened your screen share in Discord, I did not hear myself.
Oh yeah, you're probably hearing it through your screen share. Here, just mute the screen share. No worries.
Okay.
Okay,
How
sweet.
do I mute the screen share?
Oh, 1 second. There should be a. Yeah, you just close it if you need to. It's not a huge deal. I don't remember offhand. So, you've been working on what's the name of your project?
It's VADC.
VADC.
Voice activity detection in C. Very clever name. Yeah. Yep. Well, the first thing I just wanted to tell about like what's the point of the whole thing, like how it started and what it does. And I even had a cool demo prepared, but sadly we had some technical difficulties, so well, we will not be able to show you live how it sounds in the video player, but I can show you how it looks like in the audio editor. So the purpose of the whole project that I was working on, that eventually became the VAD neural network in pure C, was basically to just remove silence from long form podcasts, educational videos, and streams. But with a twist, like not just silence, but also everything that is not human speech. Because there are a lot of times there are like music intros, there are keyboard typing noises, especially in programming streams. So, and I really liked listening to programming streams, educational streams, even rants, hello handmade hero enjoyers on the go. So it was not very convenient to skip manually when Casey is typing on the keyboard and stuff. So and the simplest silence removing filter of FFmpeg did not do a good job. Like it was just detecting silence, and I wanted to remove everything that is not human speech, which is how I found my way trying out voice activity detection solutions. So let me change the screen from the video player to a slide thingy program. Okay, so this is a little bit of a spoiler. Let's start from something simpler. These are two waveforms, just a screenshot from the Reaper audio software. I just put there, I downloaded the first episode of the Unwind show with, well, we're streaming right now, so half of my brain is not working. So the name escapes me, but I really like this project of of the person that was featured in the first Unwind episode. I think he called it Quick or CUIK
Quick
/ TB backend.
Right.
Something C compiler, code generation, very cool project.
Mm-hmm.
So, and this particular episode actually doesn't have that much non-speech content. As you can see, the top result right here, this is the raw, unprocessed, unedited version. The bottom one is after I have used the voice activity detection tool and FFmpeg to remove everything that is non-speech. It is noticeably shorter, but not by much. Some streams can be cut by like 50% or more.
So this is a little fancier than just like cutting out completely dead air, right? I think you'd said you were using it for cutting out streams where there was dead air, but there's like a little music playing in the background or something. So there's some clever tricks here, right?
Yeah. Well, it's in the name, voice activity detection, right? So first I tried what was, I don't remember, something default WebRTC based, and it wasn't really good. So I kept searching until I found another solution that is the excellent Silero VAD models.
Mm-hmm.
It is a neural network trained by Silero team. I don't remember right now what is the name of their company, but the model that they released was free for the community to use or something like that. MIT license. I am not a license guy. So all I know, MIT means you can use it for non-commercial and maybe even commercial purposes.
I believe MIT just requires that you credit the people you used code from.
Attribution, right?
Yeah.
So, well, this is what I tried out, and it works surprisingly well. Well, right now at the screen, I'm showing an example output of the VADC program,
right.
the main program of my project.
Yep.
This particular one does not use the C backend. It uses the ONNX runtime backend, which is faster and which is what I currently use as my main driver.
And
But
what is
the C backend is from an older version.
Can you clarify for
it
the audience here?
It doesn't really matter.
What is ONNX?
Okay, ONNX runtime is an AI inference backend that targets all kinds of, like, it has versions that run on your GPU or on CPU. It has like direct ML bindings, all that kind of fancy stuff.
Is it like training and runtime?
I think it has training support, but it is mainly inference oriented, I think.
Okay.
Like it can do training, but well, I'm not really that deep into the whole AI world,
Sure. Yeah, no
but
worries.
from what I have seen, it was pretty rare to see ONNX runtime used for training.
Okay.
Anyway, I used it for inference, and my particular project at its current state has two backends. First one was what I began with, the old Unix runtime, because it was in the beginning it was just faster than PyTorch, which is what I initially used. But I'm jumping ahead, I guess. So anyway, I just wanted to explain what this first slide is, right? This is the output of the current program for the first Unwind episode. It shows that there are like 79.4% speech,
Yep.
which is pretty high.
Yep.
2,401 seconds of speech, and from the total of 3,000
It's pretty
something.
solid. So it's like a 20%, 20% of the airtime you were able to cut out.
Yeah, it goes from 50 minutes to 40. And that is without speeding up before. Like if you're used to listen to your podcast like 1.5x or 2x,
Oh yeah.
you get 20% before that speed.
Oh yeah. No, it's absolutely great. It's especially cool for like a pre-filter for doing things like speech to text as well, right? I've got
Oh yeah.
a big stream that I want to just kind of turn into something that I can digest. Well, all right, cut out all the silence so that the speech to text model doesn't have to work through quite as much stuff.
Yeah.
Yeah.
Well, you don't necessarily have to cut it out. You can use the markup to, like, say, make it silent,
Okay.
or use it for ducking, like automatic ducking uh, into for someone who doesn't know what ducking is. I'm not an audio guy, but I heard that ducking is when, like, you are talking over some, like you're doing a commentary, right? That you're watching some video. So ducking is when you are talking, the volume of the original video goes lower.
Right.
So automatic ducking, like, say you have voice activity detection enabled, and when you're talking, or if you have a pre-recorded talking commentary track, you can use it to automate the lowering, the fade-ins and fade-outs of the volume of the secondary track that you're talking about, right?
Sure.
Or if it's a music, or I don't know. And a very useful thing, this voice activity detection.
So
So this is basically why I started.
let's dig into the meat and potatoes a little bit. So
Okay.
you took the Silero model and made it run on top of um, your own little piece of C code, right? So
I started with Python,
you started with Python.
their
Yep.
official one. Yeah.
And you said that they had what was it? It was a PyTorch bytecode blob or something, right?
Yeah, it's a PyTorch JIT package.
Okay.
Like it's basically just Python code, but they can export it to with whatever they. I don't know why they call it JIT, but let's just keep it
Right.
for the yeah. So it's just basically it's just a zip archive with the .jit file extension, which contains all kinds of Python pickled files and stuff. I will show later what it looks like.
Okay.
So I started with that. That doesn't have a direct Python source code, but you can load it from the, like, with the PyTorch API, torch.jit.load or something, and just call inference on it
Sure.
right away. So this is how I started.
Okay. All right.
Then I
So
switched to ONNX version. The official Silero releases had released them in two formats. One is pytorch.jit, and the second, the .onnx, which is basically exported from PyTorch code.
okay. All right. So then, like, what does the process look like for going from nasty Python bytecode to C? What pieces did you actually kind of pull out here?
Well, first, first I switched to WinNX runtime because it was faster, like two
Mhm.
times or three times than PyTorch.
Sure.
It's also much faster to load. Like when you, even if you're using it from Python to spit out the timestamps where speech occurs, which look like this, by the way.
Hmm.
This is
So are
for
those
demonstration
timestamps
purposes.
in like seconds and milliseconds, or what are we looking at here?
Yeah, every line has two numbers separated by comma.
Hmm.
There are two timestamps, start and stop.
Okay.
So, example of first line, we have from 11 seconds point 17 to 11 seconds point 90, there is speech.
Right.
That's
Okay.
it. Each line is just that. And there are a lot of lines, as you can see from the size of the
Oh
scroll
yeah. Yeah.
bar. They're like it spans up to 3,000 seconds or something, like,
Hmm.
which makes it almost almost an hour,
Hmm.
50 minutes. So yeah, this is what I started with, the original Silero PyTorch wrapping surrounding code that actually called the loaded the .jit model and use it for inference. It basically outputted something like that. So I
Okay.
initially took this and converted it to an ffmpeg filter script,
Right. Okay.
which is another,
Oh yeah.
which looks like this. Yeah,
Yep.
it looks wild, but it works.
Hmm.
What it does, it, as you can see, it just spits out between operator,
Right. Yep.
and it inserts the start and stop timestamp from the previous screenshot.
I didn't realize a FempEg could take a script quite this large. It's fascinating.
Well, this is no way, this isn't really large. I actually used it to generate a filter script for at least 10 hours worth
Wow.
of audio podcast, and it worked. I don't know how, but
Hey, we'll
kudos
take it.
to the FFmpeg team
Yeah.
that
Yeah.
it just worked. It
Cool.
wouldn't if I tried to pipe it via the command line, but it uses the, like, load the filter script from an external file.
Right. Okay.
So it's not subject to maximum command line string limitation of the
Hmm.
terminals. So yeah, you could. This is basically the script that just will cut out everything that is not speech from the original audio and get you this get this top waveform to look like this bottom one.
Right. Okay. So bottom waveform is the video
Yeah,
audio that has been kind of trimmed.
yeah, the short one.
Right.
I
Okay.
can try switching to the live window of the audio editor
Oh, it's okay. This is actually
for
a
zooming.
perfectly good view.
Yeah,
And then we've got a is that an activitygram? What I forget what those are called. The your heat map below is that
this spectrogram.
spectrogram. Yes, brain's not
Yeah,
working today. Um,
same.
so you've got a spectrogram of activity in your two audio streams.
Come again?
So that if you scroll down just a little bit,
1
uh,
second.
oh,
Anyway, I wanted to switch to the Reaper window. Now I don't see it, so we'll have to do with
oh,
what we have.
okay,
Yeah.
no worries.
So okay, now here. So this is also a screenshot from the Reaper program. It shows the same audio waves, but in a frequency domain, which is
Okay,
called spectrogram.
Right. Yep.
As you can see, by the way, this part with all these green, shiny, bright spots,
Mm-hmm.
we do not see it in the bottom
Oh,
picture.
interesting. What is the green shiny spots?
It is probably the intro music.
Oh, okay. Hmm.
Well, you can read the spectrogram like at the bottom there are, I may be not, I may be misremembering, but I think the bottom, the most bottom row is the bassiest frequencies.
Okay.
And the higher you go, the shriller and the higher the frequencies become.
Sure.
And as you can see, there is a cutoff right here,
Right.
which is typical for most compression algorithms. They do not compress frequencies that the human ear cannot perceive.
Right. Is that like 18 or 20 kilohertz?
Yeah, something like that.
Right.
And human speech is, of course, way below that. And these are the bottom.
Interesting.
The bottom spectrogram is the one where we cut off all the music, where there isn't really much speech. And this is basically what the spectrogram of spoken, human spoken audio looks like,
Yeah.
approximately.
Mm-hmm. Well, sweet. That's
It
a.
is at a closer zoom level, by the way, than the top waveforms.
Oh, okay.
Like you can see the like 5, 10, 11 seconds. It's
Oh, okay.
before.
So this is just looking
Yeah,
at the
it's the
first
first 33 seconds.
yeah,
Yeah, because
half
the
minute or so.
spectrogram doesn't really look
Oh, yeah.
too meaningful at high
That's fair.
zooms.
Okay.
Yeah,
Okay. Sweet. So
but it's yeah.
what actually what exists on the seaside? So I've got a sense for like what the project is and kind of roughly what you're trying to do.
Okay.
Um, so you had to actually kind of run this model. What does it look like to run a model? You've got probably some FMAC code. You've got like give me your run through.
Yeah, there are steps for all this madness. Let's try this. Okay, before we're this does not really this does not change whether you use C or PyTorch or ONNX runtime. The process is the same. This is a very beautiful and realistic drawing of a waveform, which you have seen a
Yep.
crude rendering from the audio editor before.
Mm-hmm.
So let's think of let's look at 1 second of it, right? We have a waveform input that comes to the neural network, and we want to know where is speech in that second. Like second isn't really long enough, but it well, there are many seconds we process sequentially. So
Sure.
yeah, so this particular neural network works with chunks of length from 30 to about 96 milliseconds.
Okay.
So in 1 second, there are like about almost 10 chunks of, of these sizes.
Mm-hmm.
This also this particular uh, voice activity detection model works with audio sampled at 16,000 hertz, which is pretty typical for audio-based neural networks. I think
Okay.
Whisper transcription also uses 16 kilohertz.
Mm-hmm.
So since we're chunking it like 1 second to about 10 chunks, precise we have the precise count of samples in each chunk, which is 1536,
Yep.
which makes it almost 96 milliseconds.
Okay.
The the basic audio format is like dot wave, right? Which is a PCM format. Most commonly, it's 16-bit,
Mm-hmm.
and basically this is all just gobbledygook for people who don't work with all this stuff. But for programmers, I think it will make a little more sense, because PCM 16-bit means 16-bit integers. Oh, 1 second. I'm sorry. Alarm goes off. So the most common wave format to store is comes in 16-bit pulse code modulated format or whatever. Basically, it means that you have int 16s that describe where the wave goes at each small point in time. Like here, for example, can be like this right here can be, oh, I don't know, like something like 16,000. This goes like 20,000. This is even higher, and then it goes low, low.
Mm-hmm.
And since it's science, it can go below zero, but I did not draw this.
No worries.
I did not draw it below zero, so just for demonstration purposes. So we have this waveform, which if it is sampled at 16,000 hertz, it means that in each second we have 16,000 samples.
Okay.
Since we're talking about int 16, it means we have 16,000 shorts in 1 second.
So what do you do with those samples?
Yeah, well, first, as I said, we're splitting into separate chunks of length 1536. This isn't really static. This particular voice activity detection model can work with chunks sized from 512 to 1536, which is basically a multiples of 256.
Sure.
So first we have this chunk of 1536 samples in 16 format. Yeah. First we have to convert it to floats. I think this is trivial enough, so I don't have to explain how it is done. So
you make a big array of
we convert
F32s?
Yeah, we have F32s, and since int 16s they span like from minus 32,000 to positive 32,000.
Yep.
We want floats to go from 0 to 1, basically normalized floats. So this is one step we do. We divide every int 16 by the max positive int or something. This way we get, well, it's basically typical for neural network models to convert and normalize their input to be in the range of around 1.
Right.
Around 0,
Yep.
like -1 to 1 or 0 to 1.
Yep.
Yeah. So then we have the I'll try switching to the dynamic window. There is a little bit more after that. So after we have this chunk, we basically give it to the neural network, and we want it to give us the probability that this particular chunk has speech. Typically, in this model, the probability comes in the range from 0 to 1. So this is the high-level overview of it, I think. You just give it all the chunks from the entire audio, and it gives you probabilities for it.
Okay.
Then you have a very big list of the probabilities, which you can then use all kind of thresholding and filtering techniques to find, okay, where are the segments of uninterrupted speech.
Sure. So let's get into the kind of implementation details, because we're getting a little bit short on time. What does, like, I guess it's time to kind of break out, what does your GitHub project actually wound up doing on the crunchy side. So we've got a sense of like, okay, here's our pipeline. We've got a waveform, and we're gonna break it out into samples. Those samples get converted into floats. Awesome.
Yep.
When you want to run a model that's taking these 1 to -1 values, what actually goes into like operating on those? Presumably they're weights, right? So you're operating on your pile of weights.
Yeah.
What does that kind of look like from a kind of a stepped process perspective? You've got some start, you've got some chunk, then right.
Basically, this is all after you give to the neural network the, let's talk about one chunk for simplicity's sake.
Yep.
It has this input data of 1506 floats, right? Then it has to do a bunch of computations and basically reduce it to one floating point probability, 0 to 1.
Sure.
And the neural network inside consists of all kinds of basic arithmetic operations.
Okay. Yep.
They are mostly multiply adds,
Sure.
but they are, of course, when they get combined, they become more complex. You start with just multiplication and addition. You then grow up to use matrix multiplication, which is basically, as I came to understand, matrix multiplication somehow manages to capture really well the operations that the neurons do to process the input data. I am not a machine learning scientist at all. I didn't know any of this when I started. I was just
There's one way to
simple
learn,
guy
right? You got to learn
that
doing
likes
something.
low-level programming, and I just wanted to see, hey, maybe it would be cool to see if I can make this transfer this neural net that I like so much. I mean, I
Yeah,
transcribed
absolutely.
like thousands of podcasts with it, and
Absolutely.
I just wanted to see if I can implement it in C. And well, I didn't know what I signed up for, but it was quite a fun journey.
Well, nobody ever like starts a project going, this is going to be really painful. That's why I'm doing it. No. You start off and go like, this can't be too bad, right?
Of course.
Of course. So how long did it
Yeah.
actually wind up taking you to go from like, I sort of have a Python model working and running to I've got like a C wrapper that mostly works?
I have no idea.
No.
I don't remember.
Well, you've not been working on it for
I,
that long, right? It's a year or two.
yeah, on and off, I would say. Since, well, I can show you one interesting slide here. This is a screenshot captured from the application called netron.app, which is also available in desktop form. You can basically drag and drop the .onNX model into it, and it will show you this graph. I inverted it in the image editor because it does not have the dark theme. So it is more convenient to view for night dwellers like me. And this is basically what a neural net looks like underneath the hood.
Sure.
And as some of you may notice, this is basically like a bytecode instruction string for a virtual machine, which you can see has each node,
Can you zoom in just
each
a little bit?
box is basically an operation.
There you go.
Yep.
Awesome.
This is convolution, the last part. The names are based on whatever was in the member variables names in the Python code.
Sure.
But the last part is usually the name of the operation.
Okay.
Convolution is like one of the most common operation
And so
in the neural network words.
is this the model that you've just run here for VADC?
Well, it is a Silero model, but there is a twist.
Okay.
Like, as you can see, I can almost fit it in a couple of screens.
Okay.
Like I can do something like this, right?
Yeah.
No spoilers. Like, yep. No, you don't see nothing. Like I can crop it like this, and like, yep. Whoops. Yep. There we go.
Yeah, look, you can put
Yeah,
it basically one screen.
since it's vertical, it's a little bit uncomfortable to show at the same time. Anyway, this is a Silero model, but this isn't really a Silero model that I started with.
Okay.
This is Silero V5,
Okay.
which comes, yeah, a fun fact. There are like three versions of Silero models, at least. There's V3.1, V4, and V5. This is V5.
Okay.
And with each version, the architecture of the model was simpler and simpler. This
Interesting.
is not the model I was started with.
Okay. What did you start with?
Yeah, I started with something like
Okay. That's a little more of
this.
a model. Yeah.
Well, you may notice that it has almost the same ending, like here with two these inputs and LSTM here, which,
Sure.
by the way, stands for long short-term memory.
Mm-hmm.
Yeah, that's what the name means, long short-term memory.
Mm-hmm.
Anyway, so yeah, the third version turns out to be the most complicated of all of them because it includes, as you can see, they look kind of similar, 4 layers, which is
Okay.
basically a transformer thingy.
So they had a bit of a
Like,
refining process over the years, it looks like. They figured out what they were trying to
yeah,
do and
but
slowly pared it down.
yeah, well, since I'm not really good at, I don't, I don't train neural networks, so I have no intrinsic understanding like why one model chooses to use the transformer architecture with attention, multi-head attention in this case.
Right.
Like, how does one choose how many layers of those? Like, how does one choose this or that? Or like,
So is
why
VADC still
this big
targeting?
model works a little bit worse than this very, very simple and small one, right?
Is VADC still targeting version 3?
Yeah.
Or is it now on version 5?
Well, it's still version 3,
Okay.
but I don't think see, if I did version 3, doing version 5 is way easier.
Right.
Way easier, as you see. Like, version 4 already dropped the transformer.
Mm-hmm.
Like, there are, by the way, for those of you who do not know, transformers are those neural net AI thingies that became popular and very trendy in the recent months and years, popularized by ChatGPT,
Mm-hmm.
which, by the way, GPT stands for Generative Pre-trained Transformers. So yeah,
Mm-hmm.
I somehow managed to stumble upon my first ever uh, neural network project. It feels like I managed to choose one of the most complex ones. I don't know if it's my luck or whatever.
Well, you figured it out. It works, right? So
Yeah, it took some time, but
look, think of all the things you wouldn't
this,
have learned if you had gone with the simple stuff
yeah,
first, right?
well, yeah, well, if I saw this diagram before I started, I would probably never get started because it really
Well,
looks very scary.
that's how that kind of
But
works, yeah.
it turns out most of these nodes are kind of junk nodes. Like,
Oh, okay.
the I'll do a quick, a small spoilery thingy. Like, this whole big chunk can look in Python like this.
Oh,
Like,
okay.
if this equals this, then this, and there are like array
Right.
indexes like here, and
The code doesn't
and
look that scary, even if
yeah,
the graph
yeah, the
certainly does.
code looks way simpler.
Yep.
The original Python code. it's just basically it's like the assembly language of the neural networks.
Sure.
In particular, the Unix runtime format, but
It
they
look,
are pretty similar to other inference frameworks.
I've seen a lot of similar graphs that have negate with
Yeah.
sea of nodes on his compiler work. Trying to
So
break out like
anyway,
IR.
to finish this whole thing in, it really looked very intimidating, but in time I just started noticing patterns and
Mm-hmm.
just saw that all of this complexity is basically like 2, 3, or 4 at most very simple math operations.
Sure.
Convolution, which is basically a glorified dot product,
Right.
and matrix multiplications, which is also a glorified dot product.
Hmm.
And, and when I started to implement the most simple primitives, like in here, convolution, add, ReLU. By the way, ReLU is a fancy name for clamp to minus 0 to 0. So, like, if it's below 0, make it 0. That's all it does. Leave all positive numbers untouched, make all negative ones 0. That's it. Like, here we have transpose, which I think you can imagine what
So
it is with matrices.
is it just a clamp then?
ReLU is clamp negative to 0. Yeah,
Yeah.
there are some fancy variations like leaky ReLU that do more than that, but this particular model does not use it, thankfully, so
Hmm.
I did not have to implement it too.
Fascinating. Okay.
So once I have implemented the basic operations like convolution, subtraction, well, of course, subtraction, I did not have to implement. My VADC does not really include any virtual machines or opcodes. I just wrote straightforward C code.
Sure.
So once I have built the smaller primitive, it rapidly became like if you can imagine like me scratching off or something like that, like this done, this done, this done, this done, this done.
Right.
With each new operator or a group of operations, I started to scratch off like things in the other places too. Like I
Sure.
scratch off 1, 2 here, and everyone here also goes, right?
Well, that's the joy of
And
programming,
then,
right? You write a function
yep,
and you can reuse it,
yep.
especially when it's
When I so
math crunchy.
exactly, exactly. So when I finished one of those, I basically got to cross off all of those as well.
Oh yeah.
So it
Okay.
was really nice.
Mm-hmm. Well, hey,
Yeah.
at this point we are coming up on the top of the hour, so I want to make sure we can get some Q&A, and if we have Q&A, I want to make sure if there's anything else that you want to cover with this, we can make sure we cover it. So,
Let's see. Oh yeah. So one thing, which is kind of one small thing. This is how I was trying to learn what a matrix multiplication, how it works, how to implement it, because
oh yeah,
I could not even do that. Ignore this for a while because this is not important.
this is a lovely looking diagram,
What?
by the way.
Yeah, the first one looked much less straight. It was very like hand drawy mouse. So basically, I do not have math background at all, so I have no intuition for matrix multiplication, even though I'm kind of a game programmer, but still I did not really work with matrices that much to develop this intuitive sort of understanding.
Sure.
So I wanted to, when I started implementing, I wanted to wrap my head around like how, like what is the row, what is the column, like why do you have to flip the row and the column when you multiply one by another?
Mm-hmm.
And it was very confusing. So I just remembered there was this screenshot from NVIDIA presentation of some of their new video cards, like I think it was the RTX 2000s
Mm-hmm.
that included some tensor cores that do matrix multiplications faster. And I just, for some reason, I remembered that there were like two of those planes that came together towards some cube in the middle that got then collapsed into like a flat thingy.
Yeah.
So I started from that, started drawing, and to my surprise, this is exactly what matrix multiplication is. It is just you multiply this by this and this by
Right.
this
Yep.
element wise.
Mm-hmm.
You get this three-dimensional cube. Then you just do this plus
Okay.
this plus this plus this, and then you have this bias, because of course it's neural network concept.
Sure.
You
Yep.
have a matrix and then you have bias. Bias is just you after you do this is basically a dot product. Some of you may have noticed, like you multiply one array with another array and sum the results, and there you have it. This is the result of the dot product. This is the dot product. This is one array. This is a second array, and then they go this plus this plus this plus extra bias. That basically is trainable. What part of the trainable weights? This is the weight usually, as it is stated here, and this is the input in our example. Let's say
Okay.
those can be the samples.
Sure.
This is how I was trying to visualize in my head and learn.
Yeah. No, that's a really
And this is
helpful
just the extra
geometric
stuff
understanding.
that yeah. And the fake input rows, this is just like a flash of insight, like, hey, I remember this. There are 4x4 matrices for perspective projection and for game entities. Like, why do they have these fake ones? But this is when I understood how
Mm-hmm.
to make translation work with 4D matrices.
Mm.
Sadly, we don't have enough time to explain it in more detail, but those who understood it, great.
So I would love to get, if you're willing, I'd love to get your slides here up on the Discord afterwards, because there's some really good stuff in here.
Sure. This
Yeah.
is a short slide of what's in the JIT zip archive.
Mm-hmm.
I basically extracted the .jit file, and these are the files. They aren't all of them, but as you can see, there are a lot of Python code here, mangled, and the debug pickled whatever thing. So
Sure.
I did not have the original Python code when I started. So the first step before I started writing it in C, I needed to restore the original models Python code, which is basically, if you open any of these torch mangle files,
Right.
this is what they look like. So, and the debug ones, they, as you can see, a lot of Python binary data, but what do we have here?
You got
This
full
looks
variable
like the
names. Yeah.
original snippets of the source code that we used to generate this .jit file. So it wasn't really hard to restore almost the exact same code.
Mm-hmm.
So this was the first step. Afterwards, of course, I started to go like first the ReLU thingy, that's what I said, clamp all negative to 0,
Mm-hmm.
and up from that.
Well, sweet.
So this is basically it. I think I showed most of my slides. Yeah.
Awesome. Well, hey, let's one moment. Let's kind of lead it into Q&A then. If you guys in the audience have any questions, go for it. I will have some of my own here. Where did my pile of questions go? I don't remember. But I guess we'll start with so what drew you to Silero specifically? I know you were like, well, I want to play with this a little bit, but what kind of brought you there?
Well, it was the first. It was the first VAD model that I found after I tried the web RTC VAD or whatever it was
Mm-hmm.
called, and it just happened to be really, really good, so I stayed with it.
That's fair. Oh, here's a good community question. Do you have a good kind of handmade network biased sort of resources for someone trying to get into machine learning?
And my network, what resources?
Handmade network biased resource, like things that might work from first principles, right? Things that aren't too top heavy for getting into ML, or did you kind of have to learn it from scratch?
I mostly fumbled my own way through all of this.
Yeah.
So I don't think I can recommend anything in particular.
Okay.
On second thought, no. There are a couple of videos that after I watched them, some of them I watched before my project and some of them I watched after.
Okay.
And I cannot recommend enough the videos of, the name escapes me, of course, right now. The guy from, I think, who was working with OpenAI,
Okay.
who produced very, very good educational videos about about transformers, about how stable diffusion, how to code them from scratch.
Hmm.
I think you can, of course, the name escapes me right now,
Well, worst
but I
case, we'll stick
think
them
you
in the
can,
chat later.
yeah, but I think you can find him
Was it
by typing
Karpathy?
gpt2.c. Exactly, yeah, that's the guy, Andrei Karpathy.
Ah, okay.
His video about how transformers work, and before that, I watched the video, I think, implementing micrograd or tinygrad from scratch in Python. This is the video where he coded basically the core of the back propagating gradient thingamabob in Python, which made me understand, okay, this is how neural networks work. This is what gradient is, and it was so it was so it was such a good explanation. I was like,
Hmm.
it is like very rare to find such good explanations of this concept. Like you watch it and I understood it immediately, even though at that time I knew almost next to nothing about neural networks,
Hmm.
and it explained it brilliantly. So I cannot recommend it enough.
I sent you a link. Is that like where you got your things from, or?
Let me check.
'Cause I-
Not exactly. Let's Build GPT is another video. I was talking about implementing grad or micrograd or something like that.
okay. I mean, is this the YouTube channel at
Oh,
least?
yes.
Awesome. All right.
Basically, I think you can watch any of his videos. They probably are all very good. I watched two of his videos and both like 5 out of 5, 6 out of 5. The second one was he was I think he was explaining something about transformers.
Excellent.
Oh, no, no. The second one wasn't Andrei Karpathy. It was Three Blue, One Brown.
Blue, blue, and brown.
It was the Three Blue, One Brown's uh, visual videos about how transformers, or I think attention mechanism works.
Oh, okay.
Those I watched after I already implemented the attention and the transformer layers, and I went from, huh, so that's why it all works. So that's how it all works.
Hmm.
But I don't know if it will help people who did not wrote the attention code from scratch, like because
Sure.
his video, Three Blue One Browse videos are very good for intuitive visual understanding.
Yeah, I've seen a fair few of them. They're excellent. We got another.
So basically, watch everything by Andrew Karpathy and watch the attention slash transformers from Three Blue One Browns.
Okay.
I think they will get you on the right path to learn from first principles.
Awesome. Well, we appreciate it. One more question from the audience here. How challenging was it to work with the ONNX runtime library? Were there any challenges shipping the ONNX runtime library to an end user? So what kind of chunk of the ONNX runtime did you play with?
Well, I used the Python API and I used the C API of ONNX runtime.
Okay.
Well, the C API was typical of the C API. You had to write a lot of C boilerplate,
Mm,
but it was well worth it after you wrote the initial helpers and macros because
okay.
it like sped up the inference like at least 2 times, I think. And I managed to do it all between waiting in the queue for Apex Legends matches,
Nice.
which I was addicted at the time.
There you go. How good was
So
the
yeah,
documentation for ONNX? Was it like, well, just kind of potter with it, or did it take a while?
I didn't use it that much. I just took their example
Oh,
C
okay.
code for candy style transfer, I think.
Mhm.
I just copy pasted it into my own project and I just modified it to load another file name, modified it to work with a little different amount of inputs,
Hey, good examples are
then
worth their weight in
hooked
gold.
up everything else. What?
Good examples are worth their weight in gold, right? That's just as good as solid documentation when you're starting out.
No, it wasn't the best example, but it was good enough.
Okay.
So yeah, it was okay, I think.
All right. Sweet. Okay. Well, I think we are kind of about wrapping up point. So if there's any other questions, toss them in now. We've got one more. So let's see. Um, we went through kind of how you got here. Was there a particular interest in like silence skipping that you had? Like, I think we talked a little bit. Like you were going on some long walks. You're like, "Oh, I want to get through my podcast, but there's a lot of a lot of or it's hard to watch video streams in well on walks. I'm not watching, and dead air isn't quite as useful when you're walking, right? Um,
Yeah,
I think that's
especially when you're washing dishes.
oh,
Like when
there's
you're
that too.
walking, you have your hands free and you can use them to skip manually. But
Yeah.
imagine you're doing something with your hand and like, oh, come on, now he's typing on the keyboard, now he's blowing his nose,
Right. Yeah.
now he's just AFK, like,
Yeah.
and he put some music. So the simple silence skipping algorithms
Yeah.
of the
Yeah.
default podcast players, they don't pick it up. So
Mm-hmm. Well, we really appreciate having you on. It's been great to have you kind of go through your runway. If you could drop your notes in some point, sometime today in the Discord, we'd love to have them. They're awesome. I'm gonna move on out here. There it is. Um, Thank you for showing up for Unwind. We should have another one next month. I'm excited about next month's speaker. I think we've got a good one. In the meantime, it has been awesome. Thank you for showing up.